and 1, okay, because you only have Q, okay. So 0.5335 divided by 0.3 is 1.778. And this 1.778 is the same because either you take it from the bottom or from the top, okay, the answer will be the same. How the sequence flow in the analysis is different because at the top is a box beam, at the bottom is a white flange, but at that point, that value is exactly the same. So what we discover down here, okay, so let's compile what we have. Okay, so we know that the Q/T ratio. So what we know over here is the Q/T ratio at point A is equal to the Q/T ratio at point B, which is now equal to 0.98. Okay, and we know that the Q/T ratio at point C is equal to what? Is equal to wait, I'm lost now. Is equal to 1.778. Right? So with this, we can rightfully declare tau max will occur at point C. Okay, so we can rightfully declare that the tau max will occur at point C. So from here, we can write that tau max is equal to V over I multiplied by 1.778, and this is occur at point C. Okay, so we know that our tau max, by looking at our question, we know that tau max is 10 times 10 to the power 3. V over I 1.778. So we know that our V over I ratio is now 10 to the power 3 divided by 1.778. So this will be equal to 562 or 5.6224 times 10 to the power 3. Okay, and some of you will ask me, what units are we looking at? So this problem is in inches, so this will be in pounds per inch to power of 4. Okay, so that is our unit. So therefore, shear stress at point A is equal to shear stress at point B, which is equal to V over I Q over T. Because they share the same Q/T ratio, so what we need to do now, we know V over I, which is 5.624 times 10 to the power 3. The V over I think we got it at 0.98. So 5.624 power 3 times 0.98 is equal to 5.512 times 10 to the power 3 pounds per square inch. Okay. So like I said, a very abstract example, but it's not that difficult if you understand the concept well, between what's the definition of box beam and white flange. And all you need to do is to cover the top and cover the bottom. We could do the covering is because, remember one of the rules that we said, the first moment of area cannot intersect or cannot cross over the centroid. Okay, like what I mentioned earlier, you don't get this from textbooks. Okay, textbooks just tell you the theory part. Okay, but I go into the theory concept and directly teach you how to apply them. Okay, right. So I'll look at the chat if anyone have question. None ever so far. Now I'm going to go into the last problem. And the last problem is, before I go on to the last problem, this structure, I cannot just, the concept will not work, okay? If I will ask you a question, B, Z, it will not work, okay? And why it will not work? Because the deformation has a twisting, which will not be covered in this course. When it's vertically, it will work because if you look at the cross section, if you look at what's on the left and what's on the right, it's exactly the same, right? So when I say exactly the same, the stiffness is exactly the same. If you look at VZ now, if I were to draw a horizon or highlight a yellow line, right? The left-hand side is not equal to the right-hand side, okay? So it's like the left-hand side is stiffer. So if you look at this concept, this is a stiffer section. This is less stiff, right? So the structure will deform in twisting, which we will not cover in this course, okay? So if you see a problem like that, I ask you what is how to calculate VZ, okay, which I will not. You can't use the same concept anymore, okay? Right, so let's look at the last problem, okay? So example number, I think this is example number, what was the last example? 2. So next is example number 3. A very similar concept. Okay, so what I want you all to learn from here is a combined thin wall and non-thin wall analysis. Okay, it's a combined thin wall and non-thin wall analysis. So let me fetch the problem. Again, this has to do with Q over T ratio. Okay. Same approach. Okay. So you have a structure over here, right? So very similar to what we have, but the good thing is the top half and the bottom half, the geometry is the same. The left half and the right half is the same. Now I'll tell you what's the difference. Okay, so knowing that we are given a vertical shear, so we have a vertical shear over here coming down is By, cause a maximum shear of 75 megapascal in an extruded beam, having the cross section, determine the shearing stress at the 3 points indicated. Okay, so again, a very similar concept where we were given tau max is equal to 75 times 10 to the power 6 Pascal. Next, we have to locate the position of tau max, and it can be either at point C, it can either be point B, or it can either be point A. For now, we don't know yet. Okay. So next what we are going to do is we are going to design our shear flow. So let me highlight what's the difference. What is the difference with this problem? So we know our geometric centroid is over here. Okay. So this is our geometric centroid. So I'm going to draw an orange line. Okay, so above the orange line is thin wall. Between orange line and the green line is non-thin wall. Okay, and the same at the bottom, but our first moment of area cannot cross the centroid. Okay, so for this, we still have to design our shear flow because there's thin wall. Okay, this is how our shear flow look like, and it will go in this way. So all these are our terminal. So terminal 1, terminal 2, terminal 3, terminal 4. So from here, let's determine our Q over T ratio. So we know that for point C, it is a thin wall and it's under white flange. And we only have Q, right? Because terminal 1 and 2 are not connected, they are independent, right? So it's only Q that we have to consider, okay? So the Q at point C, so it's width, depth, y bar. So if I were to sketch our transformation, this is our y and this is our z. So the width, I'm going to deal everything in millimeters for now. So this problem, everything is in millimeters, okay? So what we have is the width is 30. Why here to here is 30? Because we know that this is 50, we have 20, so this is 30, okay? And the depth is 10. And the y bar is what? Is 30 plus 40, 70. Wait, it's 30. So the whole thing is 160. So it's equal to 80 or 160 divided by 2 minus by 10 divided by 2. So from here, it's 22.5 times 10 to the power 3. And this is millimeter cube, or this is equal to 22.5 times 10 to the power minus 6 meter cube. So we have found the Q at point C, okay? And at point B, it's also thin wall, white flange, analysis, where, oh, before we consider that, okay, let's calculate our Q, our T ratio at point C, right? I missed that. So it's 22.5 times 10 to the power minus 6 divided by our thickness. So the thickness over here, so this is our thickness. It is 10 millimeters, 0.01. And then because it's white flange, wait, 10 millimeters, because it's white flange, I put a 1 over here, okay? So this is equal to 22.5. So it's 2.25 times 10 to the power minus 3. Okay. So we know that next we're going to consider at point B. We knew that point C is not going to be the highest, sorry, we did not really know because the thickness is the smallest, remember? But the first moment of area is also the smallest at point C. Now we look at point B. So also the same thin wall. Okay, and it's also a wide flange. And then we have to determine Q. Okay. Or not we know that the shear flow is just Q. So Q at point B is equal to Q at point C, right? You have to, so initially Q at point C, we just take here. Q at point B, you now have to include this area over here. Okay, so Q at point B is Q at point C plus by the width is equal to 20. The depth is equal to 50. Right, the depth is equal to 50. And then the y bar is 160 divided by 2 minus by 50 divided by 2. So from here, you have 22.5 times 10 to the power 3 plus by 80 minus 25 times by 50 times by 20 is equal to 55. So 22.5 plus by 55 is equal to 77.5 times 10 to the power 3 millimeter cube. And this is equal to 77.5 times 10 to the power minus 6 meter cube now. Okay.